All right, let's start chapter 7. Unless there were any questions with chapter 6 stuff, we can start with that.
From homework or in general?
From homework or in general, either's fine. Once we move on, we move on.
I have a question on 11 from exercise group 614.
614.
So, I don't know if it is on page. Oh, on page 111.
111. And what number am I looking at?
11.
11. Prove triangle ACB is congruent to ADB given that AC is perpendicular. Oh, given that that's a right angle and that's a right angle. Okay, let's draw it out. So our picture looks something like this. We know that this is a right angle. We know that this is a right angle. And how do they label the points? I lost it. Just tell me, what's this one?
A, D, B, C.
And then we know those are right angles, and what else do we know?
AD is congruent to AC.
AD is congruent to AC. And we're trying to prove that these two triangles are congruent. Right? Alright, let's see. If we know that those are right angles, what else does that give us? That just gives us that their supplements are also congruent to them. Don't know that that helps us. We could make a little isosceles triangle like this if we wanted, right? Mm-hmm. And since that's isosceles, we know that that is congruent to that. Does that give us anything? And we know that this is congruent to itself.
The middle line is congruent to itself.
Yep.
Right.
Because it's the same line.
Oh. Actually, it's a different one. Doesn't make sense.
Similarly, we have that is congruent to that. And we've got this side's congruent to
So
itself.
the same.
Well, that side angle side. Look, just do the angle B.
The angle B is congruent to itself, but we don't have that this bisects the angle.
Trying to prove that ABC is congruent to AD.
Well, since we know that these angles are congruent to each other, we know that these sides are congruent to each other, and now we're done.
Wait. Oh. Yep.
Right? What? So we had two theorems about isosceles triangles. Or I shouldn't call them isosceles because we knew if we had an isosceles triangle, these angles were congruent. And then we also proved that if these angles are congruent, so are these sides. Right? And so we've got this isosceles triangle CBD. Well, we have triangle CBD. let's back up. I knew that looking first at triangle CAD, I knew that that was an isosceles triangle because those two sides are congruent. It's the definition of an isosceles triangle. Since that was an isosceles triangle, I knew its base angles were congruent, right? Now, since all right angles are congruent, and since those two base angles are congruent, these two angles are congruent.
Oh, okay.
And since these two angles are congruent, these two sides are congruent for this triangle, CDB.
Oh.
And now, this triangle is congruent to this triangle by side, side, side. So that's how you prove that. Cool. Any other homework questions?
My question is what enables us to do that dotted line in the middle?
That is our existence. That goes back to, I think, our second postulate. 2 points define a line.
Okay.
So if I had that point and that point, that defines a line. Boom.
Okay.
Or for any 2 points, there exists a line that goes through it. Okay. Any other homework questions? No? Ready to continue?
Yeah.
All right, let's continue. Starting chapter 7. All right, chapter 7 is going to be a lot more stuff about triangles, and then we're going to start getting into what are called RC constructions, which are what you've probably seen people doing when they do geometry, how they have a compass and a straight edge. And maybe you've done some constructions. Have you?
Yes.
All right, cool. Debbie?
Yeah.
Wow. They didn't share with you when they did it? How rude. All right. Let's start then. So, to begin chapter 7, we start with a definition for interior and exterior angles. So, an angle adjacent and supplementary to an angle of a triangle is an exterior angle. In other words, angle D is adjacent and supplementary to angle C. So, angle D is an exterior angle. How many exterior angles does triangle ABC have? 6. Perfect. Right? Because we could imagine continuing that line. Here's one exterior angle. Here's another exterior angle. Could have continued that line, made that one and that one, right? So there's 6 exterior angles. D is one of them. Okay? So let's read that again and make sure it clicks all the way. An angle adjacent and supplementary to an angle of a triangle is an exterior angle. Does that make sense? All right? The other 2 angles, meaning the one that's not adjacent and supplementary to, the other 2 angles of the triangle are its interior opposite angles. So angle A and angle B are the interior opposite angles of angle D. Does that make sense? Okay. So definition for interior and exterior angles. All right, so now we're going to do proof. And what we're going to prove is that the exterior angle of a triangle is always greater than either of its interior opposites. Okay? Now we're going to do 2 proofs of this. We're going to do Gilbert's proof and then Euclid's proof. So Gilbert's proof, big picture, goes like this. This says, here's some triangle, ABC, and then here's some exterior angle. We'll put a point there, D, so that we can reference it. So we want to prove that this angle is greater than this angle. Notice that this handles both cases, because I could have instead think about this exact same angle right here and prove it's greater than angle A. So I don't need to show that this is greater than angle B and this is greater than angle A, because just flipping your picture does it for angle A as well. Does that make sense? Yeah. Like if you were to think about flipping this down here, flipping A up there, then our same proof works. Yeah. Okay, so we're not going to bother proving that this is also greater than this. We're just going to show it's greater than angle B. Now, this angle has to be either greater than, congruent to, or less than angle B, right? If you have 2 angles, one of those relationships has to hold.
Wait,
it's one of our
so
theorems.
are we saying the exterior is greater than one of the interior opposites?
It's greater than both of them. Not both of them put together. We're saying this is greater than
So
angle
it's
B
greater
and this
than-
is greater than angle A.
Each individually.
Yeah, and we don't know, yeah, each individually. Good. All right, so here's how we're going to go about proving that. We're going to show that if angle B, here's my point, BCD is congruent to angle B, then we get a problem. And then we're going to show that if angle BCD is less than angle B, we're going to get a problem. And so since it can't be congruent and it can't be less than, it has to be greater than. Okay? And then we'll handle the congruent case first because then less than is real easy when you have congruent already. So you'll see how this all falls into place. So let's assume by way of contradiction that this angle is congruent to that angle. Okay? And we're going to come over here and we're going to make a point E so that this is congruent to this. With me so far?
Yeah.
And then we're going to think about this triangle. Oops, I was going for D. Need to aim at E. We're going to think about this triangle and this triangle. And notice this side's congruent to itself. Okay? So if this angle is congruent to this angle, and we construct point E so that this side's congruent to this side, then this triangle ECB is congruent to triangle ABC by side angle side. So we would get that triangle ECB is congruent to triangle ABC by side angle side. Right?
Yeah.
Now, if this triangle is congruent to this triangle, then that gives us that this angle is congruent to this angle. Let's make sure that makes sense. If this is congruent to this, then angle CBE is congruent to BCA. BCA. That's what this congruent says, right?
Right.
You all follow that logic?
Yeah.
That's why the order matters there. So, that angle is congruent to that angle. Now, this angle plus this angle is what?
Greater.
Is 90 is 180?
What's our name for that?
Straight.
This is a straight angle. In other words, a line. Which means that ABE is a straight angle. In other words, a line. How many times does ABE intersect AC?
Twice.
Twice. So we have a line intersecting a line twice. Is that allowed?
No.
No.
Wait, I'm confused why you did that. Why you went from ACE to ABE.
Why I went from... I was just naming the same line two different ways.
No. ACB to ABE.
ACB.
No, ACE to ABE.
ABE. Okay. So this angle is congruent to this angle. And this angle is congruent to this angle.
Yeah.
These two together make a straight angle. Which means that these two together make a straight angle.
Oh.
Which means that this is a straight line.
Okay.
Well, we don't have the notion of straight in our geometry, so that is a line. And it's a line that intersects this line twice. That line and this line intersect each other twice. Which we know is impossible. That was one of the earliest theorems we did. Right, Laura? You don't have to yell. You can just nod. All right. So that's why they can't be congruent. Now let's show why they can't be less than. And I'll draw separate pictures to kind of restart here. So here's D, here's C, here's B, here's A. So now if BCD is less than angle B, if this angle is less than this angle, then that means I can draw some ray interior to the angle,
That forms the same. As B.
put F there, so that this angle is congruent to this angle, right?
Yes.
So we'll call this point right here, I don't know, E. So now notice, triangle E, or this angle is congruent to this angle, right? And so now we have this angle, angle DCB, is an exterior angle of triangle EBC. and it's congruent to one of its opposite interior. What did we just show was impossible up here? So we showed it can't be congruent right here. Here we showed if it's less than, then we can make one that's also congruent, which we already know is impossible. That's why I said once we show this one's real easy.
No, if it's less.
If this angle is less than this angle,
Okay.
then we can make the smaller angle that's congruent to it, and then congruence is bad. See big picture? Alright, let's write it out. Restart. So we're going to start by creating a triangle. Try and make so the sides aren't so much the same. That didn't really do any better, did it? Oh well. I don't remember how I labeled these last time. A, B, C, and we've got E. So 1, let triangle ABC exist such that angle BCE is not such that with angle BCE as an exterior angle. Okay? Alright, so remember what we're trying to do. We're trying to make a triangle over here congruent to a triangle over here. So, 2. But where did we start? We started by assuming that this was congruent to this and coming to a contradiction. So, assume by way of contradiction that angle BCE is congruent to angle B, right? That is congruent to that. 3, let D on CE such that CD is congruent to AB. So now we're picking a point on this angle, namely D, so that this and this are congruent. Right? And that gets us our congruent, that's going to give us our congruent triangles, because this side's congruent to itself, so when we think about this triangle, it's now congruent to this one, right? Alright, so that's the next thing we're going to say for observe triangle ABC is congruent to what?
Triangle BCD. BCE. Oh, BCD.
Try again.
DC.
Order matters. DCB, perfect. DCB. We're saying that point corresponds with that point corresponds with that point corresponds with that point. Good?
Yeah.
Alright. So now, observe that's congruent to that by what? Perfect. Okay. So now we've got that these triangles are congruent. The reason that we want to show they were congruent is so that we can say that angle is the same because that angle. So that's a straight angle and that total angle is a straight angle.
Yep.
So next we're going to say, notice now since they're congruent that this side is congruent to this side. And so the sum of these angles is equal to sum of those angles. Okay? So 5, observe that angle,
ACB.
which ones were we showing were congruent? ACB. ACB, so we said ACB should be congruent to DBC. Angle DBC. Right?
Yeah. No. Wait, yeah.
Yeah, that's what this congruence tells us.
Mhm.
Just make sure I pick them in the order. If I say ACB, I need to say DBC.
Yeah.
Okay? So observe that that angle is congruent to that angle, comma, and angle B is congruent to angle BCD, and so angle ABD is congruent to angle ACD, comma, which is a straight angle.
Got the key. Straight.
It's a straight angle. All right. So 6. Then lines A, B, and AC intersect at 2 points. Contradiction. Right?
Yeah.
Now set up our next contradiction. And we'll draw a new picture for this. Make sure we label everything the same so that it's not really different from our other pictures, just cleaning it up and restarting. All right. 7. Assume by way of contradiction. Assume by way of contradiction that what?
That angle ABC is greater than, you could just say it's less than angle B.
Yeah. So first we showed that angle BCE can't be congruent to angle B. Now we're going to show angle BCE can't be less than angle B. And then so angle BCE has to be greater than angle B, which is what we were trying to show. Big picture, remember where we're going. Okay, so assume by way of contradiction that this angle is less than this angle. Okay, what does that mean? That means that I can draw an angle inside of here. I can draw a ray inside of here, sorry I should say. I can draw a ray inside of here, call it ray BF, such that this angle is congruent to this angle. Right? That's what it means for this angle to be less than this angle. If this angle is less than this angle, that means that I can construct an interior ray to give me an angle congruent to this angle. Remember those pictures?
Yep.
When we said, let's see, how did we say it? If we said that angle B, maybe extend those a little bit, is less than angle A, that meant that I could draw a ray inside of angle A so that this angle B prime is the same, is congruent to that. That's what it needs to be less than. So if this is less than this angle, then that means that there's some ray I can draw inside there so that this angle is congruent to that angle. Which makes sense, right?
Yes.
Okay. So assume by way of contradiction that this angle is less than that whole angle. So then there has to be some smaller angle in there, some ray that I can draw to give you some smaller angle so that that angle is congruent to that angle. Right? 8. Then there exists ray BF such that angle CBF is congruent to angle BCE. Nine. Then angle, so that now this is an exterior angle to this triangle. Oh, maybe I need to label that point real quick. What should we call that point? G. 9. Let G be the intersection of BF with AC. And we know that it intersects in one of those two sides because the ray is interior.
Yeah.
Okay. So let G be that point. Now we can talk about this triangle. So now we have an exterior angle congruent to one of its opposite interior angles for this triangle, BGC. This angle is an exterior angle of triangle BGC, and this angle is congruent to one of its opposite interior angles, which we showed was impossible right here. Good? Okay. Then angle BCE is exterior to triangle GBC. Maybe we should have called that A prime. Oh well. Then that is exterior to this triangle GBC and congruent to its opposite interior angle GBC. Contradiction. Right? Because we already handled that case. We said that can't be the case. 11. Therefore, if it's not less than or greater than, if it's not equal to or less than, it's greater than, right? Therefore, angle BCE is greater than angle B. And we're done. That all make sense?
Yep. Yes.
All right. Now let's do Euclid's proof of this, which I think is a lot cleaner. All right. So the way Euclid did this is he set up his triangle. A, B, C, and we'll do the same thing we did before. Call that B. So what Euclid did is he says, pick the midpoint on this segment so that this is congruent to this. Draw this line through it. Now pick a point on this line so that this segment is congruent to this segment, and pay attention to this triangle. So you have this angle is congruent to this angle because they're vertical angles. You have that side's congruent to that side, and that side's congruent to that side. So these angles are congruent, right? Or triangles are congruent. So that gives us that this angle is congruent to this angle.
That's super important.
So this angle is congruent to this angle. This angle is less than this big angle. So remember what we were trying to show. We were trying to show that this purple angle is greater than this angle. Now, his proof has technicalities that he didn't worry about that Gilbert did. There's a reason Gilbert did the way that Gilbert did it. And that is, you need to argue that this ray is interior to these angles. Just because the picture looks that way doesn't mean that it is. And so there's some technicalities that you have to argue. You have to argue that, first off, this ray, A to whatever this point is, G, AG is interior to this angle, right? That's easy because we know this point right here is between these. This point's between them, so this ray is interior. This point is on the opposite side of this point as this point. So we know this point's on this side of this line. And it's on the ray, so we know it's on this side of this line, and therefore it's interior.
Right.
Okay? I'm not going to go through all the interior stuff writing this out. I'm just going to write it out without specifying all that. And I think one of your homework problems is to justify why that point is interior. So you can do that as homework. Anyways, let's restart and let's do Euclid's proof on that one. So cleaning back up our picture, we're going to start by making some triangle with an exterior angle.
Then what's the point of the exterior angle? Oh, wait.
Showing that this angle is always greater than those two is really useful. And we'll do theorems where we use it. So, 1, let triangle ABC exist with exterior angle BCE. Same as last time. Alright. So first thing we did was we picked a midpoint on here. Remember, we're trying to construct a triangle right here congruent to this triangle right here. Because ultimately we're trying to get some angle right here so that that angle is congruent to that. That's what we're trying to do. If I can reconstruct that angle right here and see that that angle is smaller than this angle, we're done. So ultimately I'm trying to get an angle there congruent to that.
Yes.
So the way that I'm going to do that is by getting a triangle right here congruent to this triangle. Alright, so erase. Start by picking our midpoint here. A, B, C, D. So there's D. So that's congruent to that. So 2, let D on BC such that BD is congruent to DC. In other words, it's midpoint. So now, we're going to pick a point F on line AD so that DF is congruent to AD. Let F on AD such that AD is congruent to DF. Okay? Still with me? All right. Now, paying attention to this triangle, we now have there. Oh, sorry, there's one more thing. Since these two angles are vertical angles, they're congruent.
Yeah.
So this angle is congruent to this angle. Or since angle BDA and angle CDF are vertical, they are congruent. Right? So now we have two congruent triangles by side. That side's congruent to that side. Angle, that angle's congruent to that angle. Side, that side's congruent to that side. Then triangle ADB, maybe we'll just call it BDA. Triangle BDA, following how we named the angle, is congruent to triangle CDF by side, angle, side. So, if those two triangles are congruent, then this angle is congruent to, sorry, I don't know why I had that there already. It's congruent to this angle, right? So, then angle FCD is congruent to ABD, angle ABD, comma, and angle FCD is less than angle ECB, or ECD, I guess we can name it. BCD. Well, we'll say ECB because that's what we've been referencing this whole time. Right? So this angle is congruent to this angle. And this angle is less than this angle. So this angle is less than this angle. Therefore, angle B is less than angle ECB. And we're done. That's what we were trying to show. Huh? Good? Any questions on that? Ready to move on to the next theorem? Huh? I missed a step? Oh, that's a step I missed. Alright. Okay. Our next theorem. Theorem 7-2. So we'll look at a picture of what it says real quick, and then I'll write out the words. So it says in a triangle ABC, if this angle is greater than this angle, then this side is greater than this side. So if this angle is greater than this angle, then the side opposite that angle is greater than the side opposite this angle. Or maybe they do B and A. I think that's how they do it. They put a B here and an A here, trying to be consistent with how they do it. So they say, if this angle is bigger than this angle, this side is bigger than this side. Similarly, if this side is bigger than this side, then this angle is bigger than this angle. So it's an if and only if.
Is it the side opposite of the angle?
Yes. So now let's write out in words. I don't know which one they do first. I don't know what page we're on. They start out with the sides. So AB is greater than AC if and only if angle C is greater than angle B. Okay, you understand what I'm saying?
Yes.
Right. So let's prove it the first direction. 1. Let triangle ABC exist such that AB is greater than AC. Now here's how we're going to prove this case. We're going to come onto the line AB.
No, are you going to say AB is... Wait, why are you saying that?
I need to show that first thing I'm showing is that if AB is greater than AC, then this angle is bigger than this angle. Angle C is greater than angle B.
So you're trying to prove that?
Yeah, so right now I'm proving it this direction. I'm proving if this is true, then this is true. And then I'll prove it this direction. If this is true, then this is true. Remember what if and only if means?
Yeah.
It means this implies this and this implies this. Okay? So here's the big picture of how we're going to do this. We're going to pick a point over here, C prime. So that's congruent to that, which gives us an isosceles triangle here. So that this angle is congruent to this angle. Now, using the theorem that we just used, that angle is an exterior angle to this triangle BCC prime. So since that angle is exterior to this bottom triangle, it's bigger than both its opposite interiors. So this angle is bigger than this angle. That one's bigger than that one, right? Which is the same size as this one, right?
Yeah.
Which is less than this one. Remember, ultimately we're trying to show that angle C is greater than angle B. So, angle C is greater than angle ACC prime, is congruent to angle AC prime C is greater than angle B. You see all that? This big angle is bigger than just that portion, the bottom of the isosceles triangle, which is the same big as the other bottom of the isosceles triangle, which is bigger than angle B, because it's an exterior angle.
Oh.
Exterior angle bigger than both its interior opposites. So, this angle is bigger than this angle, right? That angle is bigger than that angle. So that angle is less than that angle. That angle is the same size as that angle, which is less than that angle.
Yeah, I get it.
So big angle is greater than little angle. That's ultimately where we're going. You see all that?
Yes.
Alright, so let's write it out. Working too hard to preserve my picture. That's point B. Alright, so 2. Let C prime on AB such that AC prime is congruent to AC. How do I know I can do that? How do I know that there's a C prime on this line so that this is congruent to this?
As the postulate. Sorry, I had forgotten which one was. They're saying you can create a point on any line such as congruent to its other.
I get it from this. If AB is greater than AC,
Right.
AC is less than AB, and if AC is less than AB, then that means I can draw a point, namely C prime. Sorry, this is C.
Oh.
I can draw a point, namely C prime, such that C prime is congruent to AC, and C prime is between A and B. It's a definition. So if we were to flip that, or if we were to rewrite this as AC less than AB, we're just using the definition directly. I'm not going to bother rewriting that. Okay? So that's how we get C prime here. So now we have this isosceles triangle. 3. Then triangle C prime AC is isosceles, comma, and so its base angles which are angle AC prime C and angle ACC prime, are congruent. Good? These two angles, that one and that one, are the base angles of that isosceles triangle, and so they're congruent. No, don't see it?
Yes.
We can back up for a second. We can re-show this real quick. It's not hard to show. So here's an isosceles triangle. What does it mean by isosceles? It means those two sides are equal. Right? The way that we proved that these base angles are also congruent is we said, we'll call this A, B, C, and we'll also call this point C prime, we'll also call this point B prime, and we'll also call this point A prime. And angle B is congruent to angle B prime. So since AB, side AB, is congruent to side C prime, or A prime, B prime. You see that? This side is congruent to this side. And angle B is congruent to angle B prime. And AC is congruent to A prime, C prime. Oh, AB, sorry, is congruent to A prime, B prime. AB is congruent to A prime, B prime.
No, it's AC is congruent to B prime, A prime.
Oh, AC. Thank you. A prime, C prime. So we showed AB is congruent to A prime, B prime. B is congruent to B prime. And AC,
It's congruent to C prime, A prime.
I keep
Oh, yeah. I
labeling the
did that
wrong point. It's BC.
It's A,
BC, B prime, C prime.
right.
Okay, there we go. So AB is congruent to A prime B prime. Angle B is congruent to angle B prime. And BC is congruent to B prime C prime. So triangle ABC is congruent to triangle A prime, B prime, C prime.
C prime B.
No.
C prime B prime. C prime B. No.
It's C prime, B prime, A prime.
Yeah,
I'm
C
saying-
prime, B prime, A prime. That
Just
problem.
trying to get the angles to connect themselves.
What are you guys talking about?
A is
Your
the A is
ordering
equal to
is
C
wrong.
prime.
No, it's not. AB, look at what this says.
Just trying to get the.
This is where your picture keeps screwing your guys' thinking up. I'm saying AB corresponds to A prime, B prime. Yep. I'm saying B corresponds to B. Yep. I'm saying BC corresponds to B prime, C prime.
Oh.
Yup. You want to keep tracing the triangle out the same way. The whole point of labeling it two different ways is we're tracing it out two different ways at the same time. We're saying, look, if we start here and start here, we're going to trace out the same triangle. Do. Do you see that?
Yeah.
And so, since these two triangles are congruent, then, look at what it says. It says angle BCA, BCA. So we did BCA is congruent to B prime, C prime, A prime. B prime, C prime, A prime. So the base angles are congruent. So that's what we're using to say that those two angles are congruent. Make sense now?
Yeah.
Okay. So there was a little side note. Anyways. So we know that those two angles are congruent. Now this angle is an exterior angle of the left triangle.
Yes.
And so using the theorem we just proved, Theorem 7.1, this angle is greater than that angle, and this angle is greater than this small piece, right? It's greater than either of its interior opposites. Did we say that the angles are congruent? Yes. Okay, 4. Since angle AC prime C, the base angle of the isosceles triangle, AC prime C is exterior to triangle BCC prime, comma, then angle B is less than angle AC prime C, not A prime. You good with that line? You good with that piece of logic? Good? Waiting on you, Debbie. I have to do 2 knots. Just one's not enough. Alright. So now we've got this angle, angle B, is less than this one, is congruent to this one, is less than this one. And we're done. Then angle B is less than angle AC prime C is congruent to angle ACC prime is less than angle C. 6. Therefore, angle B is less than angle C. And we proved that if this is true, then this is true. Right? Now we prove the next way. Seven. Assume angle C is greater than angle B. Now we're trying to show that if angle C is greater than angle B, AB has to be greater than AC. 8. Observe if AB were congruent to AC, then angle C would be congruent to angle B. So that can't be the case, right? Why does this mean this?
Because it's an isosceles triangle.
Right. If AB and AC are really the same long, then that's an isosceles triangle. And so its base angles, B and C, are congruent. We already are assuming that C is greater than B. So if C is greater than B, C can't be congruent to B. So if AB were really the same size as AC, this wouldn't be true. So that can't be the case. 9. Observe if AB were less than AC, then angle C would be less than angle B. Right, draw my lesson. Less than angle B by the first part of the proof. Right? The first part of the proof said, look, if this side's greater than this side, this angle is greater than this angle. So by the first part of the proof, if AC is greater than AB, angle B is greater than angle C. Which can't be true, because we already know that angle C is greater than angle B. Then AB has to be greater than AC. Right? It has to be one of them. It has to either be less than AC, congruent to AC, or greater than AC. If it's not congruent to it, and it's not less than it, it has to be greater than it. You follow the logic of that one? Let's go over with the picture. So, remember what we showed already. We showed that if in a triangle, then the angle opposite the longest side is the biggest angle. That's what the first way showed, right? Bigger side means your opposite angle is a bigger angle. That's the first part of our proof. Okay? Bigger side means bigger opposite angle. All right. So first, now we're saying, we are proving that bigger angle means bigger side. Opposite view. Right? So we start out with, let's assume that this angle is bigger than this angle. If this side were the same size as this side, then these two angles are the same big. Because that's an isosceles triangle. Which can't be the case because we already assume this side is bigger than, or this angle is bigger than this angle.
Right.
So they can't be the same size. So if this being the same size as this makes those angles the same size, then that can't be true. Right? That's what we do in a contradiction. We assume something's the case and we show it doesn't work. Maybe I should have said, by way of contradiction, assume AB is congruent to AC. Then angle C is congruent to angle B, contradiction. Maybe I should have said that way. And then assume by way of contradiction that AB is less than AC. Well, if AB is less than AC, then its opposite angle is less than its opposite angle. That's what we showed up here.
Right.
So if AB is less than AC, then its opposite angle is less than its opposite angle. So angle C is less than angle B. But we already assumed that angle C is greater than angle B. These can't both be true. We're already saying this one's true, so this one's false. Contradiction.
Right. Okay.
So if AB is not congruent to AC and AB is not less than AC, then AB is greater than AC. So I probably should have said assume by way of contradiction those things. Good?
Yeah.
Everything makes sense? Just go back and watch the lecture twice and you'll be fine. Okay. What theorem was that? 7.2? Moving on to theorem 7.3.
What about the definition?
Oh, did I skip a definition?
Skip to 120, very bottom page.
We haven't reached 120 yet.
James, you're way skipping ahead.
Theorem 3 is on the bottom of 119.
So we're doing theorem 3, and then we're going to go and do definition 7.2. Alright, so theorem 3 is a very, very famous theorem. And it is called the Triangle Inequality. In short, what the Triangle Inequality tells us is that the shortest distance between 2 points is a straight line. If I want to get from point A to point B and minimize my distance to do it, the fastest way to do it is to go a straight line. In other words, there's no other point I could go to and go here then here. That makes the trip faster.
Right.
The fastest way is always to go straight there. That's what the Triangle Inequality is going to give us. And it's Theorem 7.3. Theorem 7.3. So let's get the verbiage for it. Well, we don't need it. In any triangle ABC, AC, that length, remember when we put the bar above it, we mean the length of it, that represents a number. The length of AC is less than AB plus BC. Okay? Now notice that, okay, so now we're going to prove this. In proving this, if we don't pick AC to be the longest side of the triangle, this is already trivially true, right? If AC is not the longest side of the triangle, then obviously it's shorter than one of its other sides, and so it's shorter than the sum of the sides. Do you see what I'm saying?
You're saying we have to put that as the longest side?
Yeah, we want AC to be the longest side. So in other words, here's some triangle.
Oh, okay, I see what you
A, B, C. In my proof, if I were to, let's say, for example, make that C and this B, obviously that side is shorter than the sum of these two sides because it's shorter than this side already.
mean. Right.
Okay? So we want to take AC to be the longest side of our triangle and show that the theorem's still true for even the longest side of the triangle. So even when we let AC be the longest side of the triangle, the sum of the two smaller sides is still greater than the sum of the longest side. Does that make sense?
Yes.
Alright, so that's what we're trying to prove. How are we going to prove this? What we're going to do is come down here and pick a point B prime so that this is congruent to this. Okay? And that gives us what kind of triangle?
Isosceles.
Isosceles. So that this angle is congruent to this angle. Now look, if I can show that this side is greater than this side, I'm done. Okay? In other words, if I can show that BC is greater than B prime C prime, if I can show that this side is greater than this side, then that means that BC plus AB is greater than B prime C prime plus AB prime. Because that's the same number, right? So if this is greater than this, then this plus this is greater than this plus this.
Yeah.
And this plus this is AC, right? So the whole trick to the proof now is showing that this side is longer than this side. And we just barely got a theorem that tells us that if we can prove that this angle is bigger than this angle, we don't even need to say it's the biggest.
Right.
But if that angle is bigger than that angle, then its opposite side is bigger than its opposite side. That's what our last theorem gives us. So that's what we're going to do. You see a big picture how we're going to go about doing it?
Yes.
So we're going to create our isosceles triangle, which gives us that those two angles are congruent. Right? Then we have, this is an exterior angle. Let me just give these names real quick so I can write it out for you. So we'll call this angle 1, 2, 3, 4. With me?
Yeah.
So I now know that 1 is an exterior angle. So angle 1 is greater than angle 3. Angle 1 is greater than its interior opposite. Angle 3 is congruent to angle 2. And angle 2 is the exterior opposite to angle 4.
So it's greater than.
So angle 2 is greater than angle 4. So we have angle 1 is greater than angle 3 is congruent to angle 2 is greater than angle 4. Or in other words, angle 1 is greater than angle 4.
What was that?
Which means that the side opposite angle 1, BC, is greater than the side opposite angle 4, B prime C.
Pictures lie.
But that picture's not lying.
What do you
I
say?
can't draw a triangle without making this side shorter than those two sides put together. What do you feel like's lying there? Angle 1, does it not look like it's bigger than angle 3?
It does.
Doesn't angle 3 look like it's about the same size as angle 2?
Yeah.
Doesn't angle 2 look like it's bigger than angle 4?
Uh-huh.
Okay, that's what we said there. So angle 1 is greater than angle 4. So the side opposite angle 1 is greater than the side opposite angle 4. And now we just add the same thing to both those. We add AB and A prime B prime to both sides. And we're done. You see it? You don't? Play with your hair? Alright. So let's erase all that. Let's erase our picture. One. Let triangle ABC exist such that AC is greater than AB and AC is greater than BC, right? We want AC to be the longest side. Otherwise, we're basically just done with the proof.
Yeah.
You remember that discussion at the beginning? So our triangle, we want to make AC as big as we can, and then that's point B. Good? So that means that AB is less than AC, which means that there exists a point B prime such that AB is congruent to AB prime, and B prime is between A and C. That's what it means for AB to be less than AC. And we said AB is less than AC. Good? So 2. Then there exists B prime on AC such that AB is congruent to AB prime. Good?
Yeah.
Okay. So now that gives us an isosceles triangle.
Mm-hmm.
So we know that this angle is congruent to this angle. Good?
Yes.
Base angles of an isosceles triangle are congruent.
Yeah.
I think the name for that proof is called the Pons Asinorum. I think that's the famous name for the proof that the base angles of an isosceles triangle are congruent.
Why? The what is it?
I think it somehow comes from Latin for bridge of asses or something like that, because it makes the shape of a bridge that you take your donkeys across. Something. I don't remember exactly why, but I'm pretty sure it's called the Pons Asinorum. Alright. Little side note, irrelevant. Continuing. So we've got that the base angles are congruent, right? So then angle ABB prime is congruent to angle AB prime B by Pons Asinorum. I'm not sure how you spell it.
Isosceles triangle.
Some Latin thing. By isosceles triangle. Sure. 4. Okay. So remember where we're trying to go. We're trying to show that this side is bigger than this side.
Yep.
We're trying to do that by showing that this angle down here is bigger than this angle right here. the way that we're going to show that is with exterior angles. This angle, angle B, B prime C, is exterior to our isosceles triangle, so it's greater than its interior opposites, which are those two angles.
Yep.
So this outside angle is greater than this angle. This angle is congruent to this angle. And since this one's exterior to the right triangle, we have this angle is greater than this angle.
Mhm.
So this is greater than this is equal to this is greater than this. So this is greater than this. So this side's greater than this. That's our thinking. So, let's say that. Observe angle CB prime B. CB prime B is exterior to triangle ABB prime, comma. So, angle CB prime B is greater than angle, what did we call that last time? ABB prime? ABB prime. So this angle is greater than this angle. 5. Similarly, observe that this angle is exterior to this triangle over here. So this angle is greater than this angle. Observe angle AB prime B is exterior to triangle BB prime C, comma. So angle ABB prime is greater than B prime BC, angle B prime BC. So now put it all together. Then angle, this one, CBB prime right here, CB prime B, sorry. So CB prime B is greater than this one, is greater than angle ABB prime is congruent to angle AB prime B is greater than angle B prime BC, comma. So, if this angle is greater than this angle, BC is greater than B prime C prime. So, BC is greater than B prime C, not B prime C prime, B prime C, by our last theorem, Theorem 7.2. Right? So 7, since BC is greater than B prime C, well, we'll just say it this way. That implies BC plus AB is greater than B prime C plus AB prime, right? So if this is greater than this and we add the same thing to both sides, it's still greater. If 3 is greater than 2, then 3 plus x is greater than 2 plus x. Good? Okay? Which means it's greater than B prime C plus AB is the same thing as AC.
Yep.
You see that? Good, good, good. And that is the triangle inequality. You've probably come across a theorem called the triangle inequality in algebra before that captures the same idea. So the triangle inequality from algebra is that the absolute value of A plus B is less than the absolute value of A plus the absolute value of B. You remember that? You ever come across that? You know what absolute value means? Have you ever seen an absolute value sign? What's the absolute value?
Distance from zero. Distance from zero, yeah.
Distance from zero, that's one way you can think about it. So we're saying one number's distance from zero plus another number's distance from zero is always greater than or equal to the sum of, let me write it out instead of saying like that. So what it is the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. This is called the triangle inequality. It's the exact same idea.
Oh, no.
Let's remember, what do we mean by the absolute value of x? What's its actual definition? It is the max of x and negative x. Whichever of those are bigger is what this equals. So in other words, plug negative 2 in there. What's bigger, negative 2 or negative negative 2?
Negative, negative 2.
Negative negative 2. So it spits out negative negative 2. Put 2 in there. What's bigger, 2 or negative 2?
2.
2. So it spits out 2. Do you see that?
Yeah.
Spits out the max of whatever's bigger between x and negative x. That's the definition of absolute value. Right? Pretty simple definition. Right? Which one's bigger, x or negative x? Spit it out. It's the max of whichever of those is bigger. X isn't necessarily bigger than negative x. Well, if x is negative 7. So if x equals negative 7, then negative x is greater than x. Because negative x is positive 7. So the absolute value of negative 7 is 7. It's a negative negative 7, or 7, same thing, right?
Yeah.
So that's the definition of absolute value. So, to prove this, it's really easy. A plus B is less than or equal to the absolute value of A plus B, right? If we take A and we take the max between A and negative A, then this inequality is still true, right?
Yeah. Oh, yeah.
Maybe you should have started with a little lemma. So let's start with the side theorem. We call it a lemma if it's a theorem that helps us prove. Lemma, x is always less than or equal to the absolute value of x. Right? Is this always true?
Yes.
Yes, okay. So we won't bother proving it, we'll just use it. So A plus B is always less than or equal to the absolute value of A plus B. By taking the absolute value of A, I could have only made the number bigger. I might not have changed it, and they might be the exact same, or I made the number bigger. Those are the two options, right?
Yeah. Yep.
Similarly, this is less than or equal to the absolute value of A plus the absolute value of B, right? If I take the absolute value of B, all I could have done was made it bigger. I couldn't have made it smaller. Correct?
Yeah.
Okay. Negative A minus B, or we'll think about this as negative A plus negative B. That's less than or equal to the absolute value of negative A plus negative B is less than or equal to the absolute value of negative A plus negative B. Same exact thing we did up here, right? But I can rewrite this as absolute value of A plus absolute value of B, right? Absolute value of negative A and absolute value of A are the same thing. And absolute value of negative B and absolute value of B are the same thing.
Yes.
Right? And then I could have rewritten this a different way. I could have rewritten this as negative A minus B. Right? So I showed negative A minus B is less than or equal to the absolute value of A plus the absolute value of B. And I showed that A plus B is less than or equal to the absolute value of A plus the absolute value of B. Right? Now, what is the absolute value of A plus B? absolute value of a plus b is by definition the max of a plus b and negative a minus b, which we showed both of those are less than or equal to the absolute value of a plus the absolute value of b, right? If this is the max, we showed it. If this is the max, we showed it. Therefore, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Very useful theorem. Comes up in a lot of places. The triangle inequality. Came up in geometry, comes up right here.
So
Very useful. My calculus class that we're doing on the side, we just barely had to use this to prove a theorem for integration.
Wait, you're doing calculus class too?
Yeah.
You're teaching it or you're taking it?
I'm technically taking it, I guess you could say. We're just getting together and going through a book. Now, Brother Claw is the one
Doing it?
that's formally teaching it, but we're just going through a book.
Oh.
And then we did it with Joanne and Alice Nicole, who are both supposed to be in this class as well, but like to left, in particularly Joanne. Alice has her finals because she's doing college classes. Anyways, not that you need any of that information. So that's the triangle inequality. Now the book moves on to what are called, or what the book calls, RC constructions. And he's using the actual letters RC constructions. R stands for ruler, C stands for compass. Now when we say RC construction, we don't mean a ruler that you're used to that has little ticks for measurements on it. We typically say a straight edge and a compass. So you might have noticed in geometry, people like to use straight edges and compasses to try and help improve things. Why? Oh shoot, I'm jumping the gun. We need the definition of a circle, and then we'll come back to this.
So we're done triangles?
I skipped the definition of a circle. I don't know where we are, I just know I need to talk about circles before I see constructions. What page are we on? My book keeps jumping.
120.
120. Oh, I skipped a couple definitions. Alright. We need to go through 4 definitions and then we'll talk about RC constructions. So, forget that for a second. Alright, first definition. I won't write it out all the way. So, first definition says that if we have points P1, P2, we have just endpoints P3, dot, 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 dot. There's a little fly right in front of my face that is just hovering around. Driving me crazy. Alright, all the way to Pn. So we have endpoints here, right? So if I have endpoints and I draw all the segments, P1 to P2, P2 to P3, P3 to P4, P4 to P5, to P6, to P7, to P8, to P9, all the way to Pn, whatever. Are you comfortable with this idea of Pn? I'm saying some number,
Yeah.
and it can be any number, it can be
Yes.
any natural number. So anything from 1 to, no, you can go past that. Any natural number is the best way to say it, not including 0, depending on your definition of natural numbers. So we call this,
There was actually a fly in my
yes, there's actually a fly, I'm not lying. All right. Sorry about that. Anyways, so if we have some number of points and we connect them with the line segments from point to point to point to point to point, this creates what's called a polygonal path. And you might remember from graph theory talking about paths. Same idea. It's a polygonal path. Now, if Pn and P1 are the same point, so in other words, if the last point in your path is also where you started, so this is Pn minus 1, this is the second to last point, and Pn and P1 are the same point, so this shoots back like that, then you have what's called a polygon.
Okay.
So if it doesn't end where it starts, we call it a polygonal path. And then if it ends where it starts, we call it a polygon.
Alright.
You like my polygon? That is a polygon. Here's another polygon that you might be more comfortable with.
Okay.
If those are 4 points. Those are both perfectly valid polygons. Nothing wrong with them.
There's something
Except for
wrong
one's
with
obviously more beautiful.
I think it's the first.
Okay. So that's the definition of a polygon. It's all the line segments connecting all the points in a polygonal path. You're good with that? Okay. Now the length of the path is the length of this segment plus 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 the length of this segment.
And the last one.
And the last. I would say for the path, not for the polygon. So ignoring this one, making that one Pn again. So when we have our path, and even if it did go there, then sure. But you just add up the lengths of all the different segments to get the length of the path. Good?
Yeah.
And then, so pretend that this is our path again. We have a little corollary right out the door that says that the length of this crazy path is less than or equal to the length from here to here.
Is less than or
How?
We could divide that up into a triangle right there. We could divide that up into a triangle right there, that up into a triangle right there, that up into a triangle right there. And this side has to be smaller than those two sides. This side has to be smaller than those two sides. This side has to be smaller than those two sides. This side has to be smaller than those two sides. So this length is less than this length plus this length plus this length.
I thought you were saying the opposite.
Oh, did I say it backwards?
Yeah.
Okay. Da, 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 da. So now, definition of a circle. You already have intuition for what the definition of a circle is.
Decide this.
So given some point, A, and some number greater than 0, R, equal to some number, a circle is the set of all points that are R distance away from A.
Right.
So if we're given a point and some distance, a circle is a set of all points that are that distance away from A. The distance from A, which we call the center of the circle, to any one of those points we call the radius.
Radius?
The radius. Well, let's just go over all the points he makes in the definition exactly. A circle is determined by a point O, called the center, and a positive number R. The circle is a set of all points A, so we start out with O, and some positive number R. Then the circle is a set of all points A, such that AO is the distance AO is equal to R.
What's R?
Some positive number. The radius of the circle. In other words, a circle can't have a 0 radius, a circle can't have a negative radius. So with a positive number in some point, we can create a circle. Right?
Yeah.
So if I were to ask you, with a point, to draw a circle centered there with a radius 3, is that possible to do? Yes. If I said, draw a circle there with a radius 0, could you do it?
Mm-hmm.
No. If I said, draw a circle there with a radius minus 3, could you do it? No. So it doesn't make sense. So a circle, we need a point, which we call the center, and some positive number R, which we call the radius. Then the circle is a set of all points whose distance from O is R. That make sense? Okay. Read the definition one more time. A circle is determined by a point O called the center and a positive number r. The circle is a set of all points A of the plane such that OA, written like this, is equal to r. If A is a point of the circle, then the segment OA is called a radius of the circle. So here's a radius of the circle. We have some other point here on the circle. This is also a radius of a circle. Of the circle, right? And this is also a radius of the circle.
Does the circle include all the points inside of it?
No. They are all the points whose distance is equal to r. What's the distance from here to here?
No.
Less than r. What's the distance from here to here? Greater than r. And that's how we're going to define the interior and the exterior of a circle. Does that make sense?
Yeah.
So if AO is equal to R, A is on the circle. If AO is greater than R, A is exterior. And if AO is less than R, A is interior. So pick any point that you want, and we'll call it A. If A is right here, then that distance is greater than R, so A is exterior to the circle. If we pick A so it's right here, then that distance, the length of OA, that segment, is equal to R, so A is on the circle. If we pick A so it's right here, then this segment's length is less than R, and so A is interior to the circle. Good? So that's how we get interior, exterior, and on the circle. That's our definition of the circle. All right. And then some more vocabulary about a circle. If A and B are 2 points on the circle, and the segment from A to B goes through O, then we call the segment AB the...
Diameter.
What do we call it? Yeah, the diameter. My goodness. All right. If A, B are 2 points on the circle, and they don't go through O, maybe we'll say A prime and B prime, and they don't go through O, you know what that's called? A chord.
Yeah.
That's called a chord, because you can plug it in. Right? Chord.
Chord.
Because you can plug it in, like on a vacuum. Chord. I don't know why it's called a chord. But that's what it's called. A chord. C-H-O-R-D. If we instead talk about a line that intersects a circle at 2 points, that line is called a secant line. And then if we draw a line that intersects the circle at 1 point, that line is called a tangent line.
Why is that?
Why is it called a tangent line?
Tangent's the slope, right?
Yes.
So, like, explain why is it?
We won't get into that right now because they don't know what the trig functions are.
Well,
That's a trig question.
I know.
You need to learn geometry before you learn trig.
You're so welcome.
We can't go into that right now because these guys don't know what sine, cosine, and tangent are.
But I do in March.
We do.
You do?
Yeah. Well, sort of.
What's the definition of sine?
I don't know.
Okay, see?
I know.
It's the last thing we learned. It's
You don't even deserve to know that. No, we can go over that after class if you want. Okay,
Stop.
so that's a circle. Now we're ready to talk about RC constructions. Such a terrible way to learn the trig function.
We had to learn it fast because we were going and testing it to teach it to us.
Yeah, I'm sure. How Masada's textbooks are. Okay, So now we're going to talk about RC constructions. Now what does RC stand for?
Roller compass.
Straight edge and compass. That's what you get to use. Straight edge and compass, right?
Yeah.
Okay. So now back to the question. Why, when people are making construction in geometry, do they use a straight edge and a compass? Isn't that just so random?
No.
No. You draw circles.
You draw an angle.
A compass doesn't measure degrees, though. Do you all know what a compass is? It always points north, right?
No.
No, that's not the type of compass we're talking about. We're talking about it's shaped like that, and it has an end that can draw, and you can rotate it to draw a circle.
Yes.
This is a compass. You insert a drawing utensil right there, you stab into the piece of paper, and then you rotate it, and it draws a circle, right? So that's what we mean by compass. And by a ruler, we mean a straight edge. It doesn't have any measurements. You don't get a measure in our geometry and talk about 1 inch.
Right.
Okay, so why are these the things that we use to prove?
Because we could create
Make it
triangles out of
precise.
Why not other tools? Why are those the only things we use to prove? It's a historical fact, and it comes from Euclid's postulates. So far we've been talking about Gilbert's postulates, right? Gilbert was 100 years ago. Euclid was 2,100 years ago. Big gap between them. So geometry is much more exact now than it was in Euclid's time. Euclid gave his postulates. So his postulates are, in short, number 1, 2 points define a line segment. If I have 2 points, I can draw a line segment connecting them. Notice you can do that with a straight edge.
Right.
Number 2, if I have a line segment, I can extend it as long as I want. Notice again, you can do that with a straight edge. If I have my straight edge and it's this long and I draw that line segment, I can move it over a little bit and draw further. Move it over a little bit and draw further. With my straight edge, I can draw as far as I want. Number 3, Euclid said that if you had a line segment, you could pick one of the points, call it the center, and draw a circle centered at one of the endpoints with radius equal to the length of the segment. Number 4, he said right angles are congruent to right angles. And number 5, he said something logically equivalent to, if you have a line and a point not on the line, there's only one line you can draw through that point so that these 2 lines don't intersect. In other words, I can't draw another line, otherwise it will eventually intersect. These were Euclid's 5 postulates. We're using a lot more postulates than just these 5 because these aren't as exact as ours are, right? Well, he also had 5 axioms, which we don't get into that. The point is, notice which of these tell us that we can construct. This one told us that if we have 2 points, we can construct them with a line. We can construct a line segment between them. This one told us that if we had 2 points, or if we had a line segment, we could extend it. This one told us how to create circles. Notice these are the only 3 that tell us how to build things. The other ones just tell us properties. And he also has 5 axioms which just tell us properties. These are the only ones that tell us how to build things in our geometry. And notice that you can do them all with a straight edge and a compass. So when you are using a straight edge and a compass, you are using these 3 postulates over and over again. That's what you're doing. Every time you use a straight edge and a compass, you're using these 3 postulates. Now we're developing a geometry using Gilbert's axioms, but it's logically equivalent to the geometry Euclid was capturing. And so we can still use these tools to help us think about our own pictures, or our own proofs. Okay? So that's where it comes from. So let's get you comfortable a little bit with how Euclid did it. Maybe I'll give you his 5 axioms too. Euclid's 5 axioms were 1, if equals are added to equals, the result is equal. So in other words, if A is equal to B, then A plus C is equal to B plus C. Number 2, he said if equals are subtracted from equals, the results are equal. So if A equals B, that means A minus C is equal to B minus C. He said, number 3, the whole is greater than the part. I don't know how to draw that with math. The whole is greater than the part. Number 4, he said, I can't remember all these. Oh, if two things are equal to the same thing, they're also equal to each other. So if A is equal to B and C is equal to B, then A is equal to C. And then finally he said things which coincide are equal. So in other words, if I draw a triangle like that, and I draw another triangle right on top of it, and they perfectly coincide, then that means those two triangles are equal. Does that make sense? That's it. That's all Euclid's assumptions. And then from here on out, he proves. Notice these don't tell you about anything you can construct. These just tell you relationships. These just tell you relationships or that uniqueness. These are the only ones that tell you how to construct. So we'll just do 2 proofs real quick, Euclid style. So we'll do his first 2 theorems to get a feel for using these types of things to do all our proofs. So Euclid's first theorem is that given a line segment, an equilateral triangle exists whose side lengths are as big as that line segment. And he uses these to prove it. So what does he do? He goes here and he draws a circle centered at this point.
I feel like you're missing something.
We didn't go over definitions.
Oh.
They already know what a circle is. You can just use the same definitions we've always been
Keep
using.
going.
Then we go here and we draw a circle centered at this point using this as a radius. So this circle was centered at this point using this as a radius. Now we're going to go center at this point, use this as a radius. We're going to mark this point. Notice, well, pay attention to this triangle. This segment and this segment are both the radius of this circle. So this is congruent to this. This segment and this segment are both the radius of this circle. So this is congruent to this. And if this is equal to this and this is equal to this, then they're equal to each other using one of his axioms. If 2 things are equal to the same thing, then they're equal to each other. And so it's an equilateral triangle. You get a feel for that? Let's do one more. His next theorem tells us how to pick up our compass and move it. So in other words, it tells us the next theorem is that if I have a line segment here, then I can come to some other point and draw a line segment the same big. That enables us to move our compass. So I can take my compass and have it a certain length here, then I can move it to some other point and get it back to that same length. So it makes that if I have a certain circle here, then I can move here and I can draw a circle the same size. That's what it gives us. So we're going to prove it, but his theorems are very constructional focused. Because that's how he develops his geometry, using his postulates over and over again. So let's get a feel for that one. So his second theorem says, if I have some segment and some point, then I can draw a segment from this point the same long to this as this segment. You understand what we're trying to prove? All right. And we're going to use, surprise, surprise, the previous theorem. First thing I know, using postulate 1, I can connect these 2. Right? Postulate 2 says I can create an equilateral triangle this big. There's my equilateral triangle. And I know this side's equal to this side, equal to this side. Right?
Right.
Now, we'll put 2 links here. I can come to this point and draw a circle. With this is my radius. Here's my radius, here's my center. Center, radius, gonna draw a circle. You with me?
Okay.
This one gets a little bit messy, so I'm gonna try and make my steps obvious as we go. So here's my Oh, that was terrible. Should have one of you guys do this. Whatever. So, using a point and a segment, I can construct a circle, number 3. Then, I can extend line segments indefinitely. Here's a line segment. Using number 2, I can extend that. So I'm going to extend this line segment up here, which gives that this line is the same big as this line. Good?
Yep.
Now, give me my pink circle centered here, using this as the radius. So, pink circle now, coming in. See that?
Yeah.
That was, again, using postulate 3. Using postulate 2, I can extend this segment. Right? And my picture is lying big time here. But now this segment is the same big as that segment. And we'll see why. This is the same big as this because they're both radius of the pink circle. This is the radius of the pink circle. This is the radius of the pink circle. So this piece is the same big as this piece. Well, I know that's as big as that. And so the remainders have to be the same big.
Right.
Using his axioms, equals subtracted from equals leave resulting equals. With me?
Yeah.
So we just barely made a line segment at the given point congruent to the given line segment. And that's how we can pick up and move our compass. So now we know we can do that. And he continues his postulates in this way, very construction based. So this is why we use these types of constructions in geometry. It's because we're using these axioms, or these postulates of Euclid's. That's why he would use them. Now, these these RC constructions, unfortunately, we can't use them to prove everything that's true in our geometry. Three examples of problems that the Greeks tried forever to solve with RC constructions that it turns out is impossible to do. One of them is trisect an angle. In other words, if you have an angle, draw two rays so that that angle is congruent to that angle is congruent to that angle. Trisect it, split it into 3 equal pieces. You cannot do this with just an RC construction. Proving why is well beyond the scope of this class. But the point is, only RC constructions are very limited. So we're able to prove things in our geometry that we couldn't have proved just with RC constructions, is my point. Another one, so the Greeks tried forever to do this. Turns out you can't do it with just RC constructions. Although it is true in our geometry that you can trisect an angle. Another famous one, it's either called circling the square or squaring the circle. But if I give you a circle, or a square, I can't remember which one, we'll pretend it's called squaring the circle. So if I give you a circle with radius A, the job is to construct, or not radius A, area A, then the job is to construct a square that also has that same area. Turns out, can't do it with RC constructions. And then the Greeks also had a way of doing 3-dimensional geometry. They weren't just stuck in 2 dimensions. And the last one's a 3-dimensional proof. The last one that they were stuck on forever and can never figure out, because it turns out it's impossible, is if I give you some cube, construct a cube that has exactly double the volume. That cube has exactly double the volume of that.
Well, how is that impossible?
With RC.
It's not impossible for this to be true. It's not impossible for this to be true. It's not possible for this to be true. It's impossible to prove this with just RC constructions. It's impossible to prove this with just RC constructions. And it's impossible to prove this with just RC constructions. So it's limited. But they're still very useful. Good?
Yes.
All right. So we're going to get into RC constructions a little bit for the remainder of Chapter 7. And he talks about a ruler and a compass and definition. To make a ruler and compass, or in other words, RC, construction, is to draw a picture of a set of points using only a ruler and a compass. The ruler can only be used to draw a line through 2 points. The compass can only be used to draw a circle with a given center and radius. That's what we mean by an RC construction. Alright? So first RC construction he wants to do is copying an angle. So copying an angle of a triangle. So if I have some angle A